Hey everybody, this video is the beginning of our Luminal introduction series. Basically, the idea is to give you a high-level overview of the technology so that you can have a faster onboarding process. So, the thesis behind Luminal is that we are able to search through the space of equivalent kernels, find the one that's the fastest, and return this to the user. So, one of the critical steps here is being able to create a search space that has all equivalent kernels. The technology that we use to do this is what I have in front of you, egraphs, and specifically egglog as a way to interact with egraphs. From a high level, the idea here is that we're using rewrite rules to take an equation and translate it into multiple different equivalent equations. So in this example here, I've just written out a times 2. You can see on the bottom right how this is represented inside of the egraph. Now, for our case, we want to find all of the different equivalence equations, and the way that we tell egglog what's equivalent is with these rewrite rules. So you can see these first two are just the commutative rules. So we have a times b is equal to b times a, adding a plus b is equal to b plus a, etc. And then here we have kind of a hardware rule, right? So if you're multiplying any number by 2, this is the same as bit shifting that over by 1. And so the way that we can start to expand our search space is we run on the graph these rewrite rules. So I'll go ahead and run it and then explain what's happening. So you can see our graph got bigger. We added in 2 more elements into this dotted line group. So each of the dotted lines is called an E-class. An E-class holds all of the operations that are considered to be equivalent for the rewrite rules. So in our case, what it did was it went through these rules, and let's start with the add, right? It saw that any number multiplied by 2, which you can see here is what we gave it, is equivalent to adding that number to itself, which is exactly what our graph represents. It also went through and it saw our commutative rule, a times b equals b times a, and so it added that one as well. The key idea you're seeing here is that we did not delete the original node, and so this shows you how egraphs are able to contain a huge amount of information. Now, hash consing is a critical part of how we avoid having this space explode. Hash consing is the idea that if we have the same information twice, we're only going to represent it one time. So you can see here, this multiply has different left and right values. And because egglog does not want to assume everything is commutative, it's going to represent that differently than the node that has different left and right ones, even though they're all the same E nodes. Now, at the same time, when I run this a second time, we're not going to see the number of moles duplicate because we already have this information in the graph. Instead, what appears is this bit shift. Now, why did that bit shift appear only now? This is because in our rewrite rule for the bit shift, the left-hand part that it matches onto expects the number 2 to come first and the input to be on the right-hand side. Now, the way that we wrote this meant that we had to, as a first step, figure out that we could commute this num2 in front of a. And then, after we've applied it on the second run, it matches this rule. So, the big picture here is that the way that we write these rules has a big impact on how long it takes for our egraph to find certain permutations. There's another piece that I should mention, although I don't have it in the example, and that's that this search is done in polynomial time, which means that the bigger this left-hand term is, the longer and more computationally expensive it is to execute. So when your rules are running, you want to make sure that you chop them up into as many small rules as possible to avoid this kind of pain. Yeah, that's more or less the high-level concepts for egraphs. Thanks for watching.